Okay, Assalamualaikum warahmatullahi wabarakatuh and good morning. So now we continue. Okay, we just revise back again that pipe in series that I have. Okay, you have learned in last week, last class. Okay, in Monday. Okay, so now we look at the pipe in series. Okay, so we just learn more, revise. Okay, more about the pipe in series. Okay, they have the tank A to the tank B here. Okay, so the pipe in series, the pipe is okay based on the series. So they have the pipe 1, pipe 2 and pipe 3. Okay, according to continuity and the energy equation, so the following relation apply to the pipe in series. So the basic assumption for pipe in series is you must know that the total Q based on this pipe. So Q is equal to Q1. So this is Q1, Q2, and the Q3. Okay, and the HL1, HL2, and HL3. Okay, based on these three pipe. Okay, pipe in series. So that's why Q is equal to Q1 is equal to Q2 and Q3. Okay, HL is equal to HL1 plus HL2 and HL3 and so on. If the pipe is there, the 4 or 5 pipes, so in series. So this is plus. Okay, so this is the basic assumption of pipe in series. So we look at the example here. Okay, two reservoirs were connected by a pipeline. Okay, 150 mm diameter, 6 meter length, and the pipeline. Okay, two. Okay, 255 mm diameter and 50 meter length. Okay, so inlet and outlet of pipes are categorized as a shaft. Okay, and the Z is 6 meter. Okay, table or losses, calculate the rate of flow and sketch EL and HGL for the system. Okay, take F is 0.01 for both pipe. Okay, actually this figure for this example is like this. Okay, so from the tank A here and to the tank B here. So they have the delta ZA minus by ZB is 6 meter. Okay, and D1 and also L1 is based on this. Okay, so D2 and A2. So they have the from the small pipe to the big pipe. Okay, so you have this is entrance. Okay, so this is sudden enlargement. Okay, so this is the H. Okay, out. Okay, for the HM. So this is H entrance. So they have the H sudden enlargement. Okay, S E. So I just put the SE and have the HF1. Okay, HF1 in the pipe 1 and the HF2 in pipe 2. Okay, so they have 1, 2, 3, 4, 5. Okay, 5 HL. So they have the 5 HL. Okay, head losses. So this include HF and the HM. Okay, so now we just use the continuity equation based on this formula. Okay, the continuity equation for the basic assumption of the pipe in series. Okay, so we know that the A1 V1 is equal to A2 V2. So the V1 is equal to A2 divided by A1. Okay, power of square. Okay, square A2 or A1 square V2. Okay, so actually from this, so we know that A1 V1 okay, is equal to A2 V2. Okay, so we get the V1 is equal to V1 is A2 A1 V2. Okay, so you get the V1 here. Okay, so V1 A2 A2 A1 and V2. So you get the value here. Okay, so you get the value. Okay, so you get the value here. Okay, so the So you get the A1, V1, A2, V2. Okay, so you get the A2. So no 2 here. Okay, so you get the, actually this is A1, V1 is equal to A2, V2. Okay, so to get the V1, so you get the A2, A1, V2. Okay, so you get this formula. Okay, so this one. Okay, so there's no A2 here. Okay, so then you get the A2 and A1 here based on the diameter. Okay, the diameter 1 and diameter 2. Okay, so you get the A2, A1 is based on the, you must find the A1. Okay, is 5D1 squared over 4. Okay, so the A2 is 5D2 squared over 4. Okay, so you just put the A2 and A1. So you just put the, okay, so you know that the V1 is equal to A2, A1, okay, times by the V2. Okay, so you know that the A2 is pi D1. Okay, A2 is pi D2 squared over 4. Okay, and divide by pi D1 squared over 4. Okay, so you get the D1. Okay, so you get the, this is, you must, okay, so you get the times by V2 here. Okay, so you get the D2. Okay, so you get the D2A2. Okay, so you get the D2 D1 over V2. This is squared. Okay, so you get the V1. Okay, so you get the D1 is based on the D2 is, you know that the D2 is 2 mm. Okay, 2 mm diameter. So 0.25. Okay, so 0.25 0.255 divided by 0.15. Okay, so you get 0.7. So you get, okay, so you get 2.89. Okay, so that's why you get 2.89 here. Okay, so that's why you get 2.9 here. Okay, 2.89. Okay, actually, so you just, okay, just correct that. So you get that this is D2 over D1 squared, okay, times by the V2. Okay, so actually you get the 0.255. Okay, 0.255, 0.255 divided by 0.150 squared. Okay, so that's why you get the, so this is V2. So you get the value of 2.89 V2. Okay, so you get the value here. So just correct this. Okay, for, so you get the 2.89 V2. Okay, so now you know that the entrance, so the entrance is here. Okay, the HE here. Okay, so the entrance, so we just put the HE. Okay, and fluid friction HF1, expansion is HSE. okay, based on the SE here, HSE, okay, okay, and the HF2, and the exit is the HO, exit O out, okay, so exit out is this one, okay, for the minor losses, okay, so you get the here. Okay, so now the entrance, we know that 0.5 V1 squared over 2G. Okay, okay, and you get the value of this is V2. Okay, okay, and this is F1, L1, V1 squared, and this is D1. Okay, so this is V2 squared. So this is in terms of V2. Okay, so this is V1 is V2. Okay, so the sudden expansion is based on the formula in chapter 4. Okay, so you just refer to that chapter 4. So you get the value. So you get the value. Okay, this is 2. So I just clear that number. Okay, in case you can see that the number. Okay, HF2. So there's F2, L2, V2. Okay, so you get the V2 squared here and the V2. Okay, and the H out or H exit. Okay, so you get the V2 squared. Okay, so you just total up of this head loss, total head loss. Okay, so you get the head loss, total head loss. Okay, so you get the 12.64 V2 squared over 2G. Okay, so you get the value here. Okay, and then you just solve using the Bernoulli equation between 1 and 2. Okay, so you know that the between 1 and 2 is based on between the A and the B here. Okay, between A and B. Okay, actually the between A and B. Okay, so you get that this is 0. So this is 0. Okay, and this also 0 and also 0. Okay, so this is PB. Okay, PA. Okay, so you get the VA and the VB is also 0. Okay, so you get the value here. So the Z1 minus by Z2. So Z1 minus by Z2. Okay, so Z2 is, okay, we know that the Z2. So ZA to, sorry, ZA to ZB. Okay, so ZA to ZB. Okay, so this is A, ZA, and this is ZB. Okay, ZA minus by ZB, so we get the 6 here. Okay, so actually this is the ZB is 0. Okay, ZA is 6. Okay, so that's why the ZA minus by ZB is 6 minus by 0. So you get the 6 here. Okay, so the only have the HL. So total F is this value. Okay, so you just solve these equations and then until you get the velocity 2 is in this value 3.02 meter per second. Then you just put the velocity at the Q here. So A2 times by V2, so you get the value here and you get the Q is 0.154 meter cubic per second. Okay, after you get the Q, so you use the V1, okay, to solve that you get the V1. Okay, so you solve that the V1 here 2.89 times by the V2, so you get the value of V1 here. Okay, so you get the value. Okay, and then you sketch. Okay, after you solve that, you must sketch the energy line here. So the energy line is the blue line here. So you get the energy line. And the red line here is hydraulic grade line. So you just sketch the EL and HGL. So you get the 3 marks. Okay, so 3 marks for these sketches. Okay, so now we look at example 5.6. Okay, this is the pipe series, but they have 3 pipe here. Okay, pipe 1, pipe 2, and the pipe 3. Okay, so the characteristic of these 3 pipe is based on this table here. Okay. Okay, so you look here. So the L1, D1 for pipe 1, and pipe 2 is L2, D2, and pipe 3 is L3, D3. Okay, and the delta Z is from ZA to ZB is 10 meter. Okay, so ZA minus by ZB is equal to 10 meter. Okay, so the EL, this is energy line, and the HGL is the blue line here. Okay, so the pipe 1, pipe 2, and pipe 3, they give you the L length, they give you the D, they give you the E over D and F. Okay, so you find the value here. Okay, actually E over D is given. Okay, E over D is based on the cast iron. E is 0.00025, and then divide by the diameter, so you get the E over D. Okay, and to find the F, so you must find from the Moody chart. Okay, so if F is not given, okay, so if F is given, so you just use this F. Okay, if not given, you must find the F from Moody chart. Okay, based on the Reynolds number and E over D. Okay, but for these questions, they give you the E over D and F. Okay, so they give you here. Okay, so use the from continuity because this is pipe in series. So you use the V, so you get the A1 V1 is equal to A2 V2. Okay, so you get the velocity 2 in terms of V1. So you get the formula 1. So you get the A1 V1 is equal to A3 V3. So you get the velocity 3 in terms of velocity 1. So you get this formula. Then using the energy equation between A to B here, so you just draw this. You just do the equation here. Okay, actually the HF1, HF2, and HF3 is from the right side here. And then you just put to the left side here, so you get the negative. Okay, from the right side, you just put to the left side here, so you get the negative. Actually, this is the HF. Okay, total HF from the right here, you just put the F to this right, this left side, so you get the negative here. Okay, so you just put the, and the PA is 0. Okay, and VA is also 0, PB so 0, and VB is also 0. So they just have only the ZA minus by ZB, so you get the 10 here. Okay, and the PA is 0, and also put the HF1, HF2, and HF3 is based on this value and this formula and this formula. Okay, and then you just put all the value here. Okay, L, D, F in this formula, and you solve this formula and you get the velocity 1 is 1.183 meter per second, and you get the Q is based on Q is equal to A1 V1, so you get the value of Q. Okay, so this is the calculation step by step for pipe in series. Okay, this is the 3 pipe in series. Okay, so now we look at the pipe in parallel. Okay, pipe in parallel here. Okay, the pipe is depth from the A to the B here. So the pipe is a pipe 1, pipe 2, and the pipe 3. So this is the parallel. Okay, so in Malay is called selari. Okay, so the selari. So the pipe selari. Okay, so this is using the concept basic assumption of the pipe in parallel. So you must know that the total Q in this pipe is Q1 plus Q2 plus Q3. So you get this formula. Okay, so you get this basic assumption of Q. Okay, so Q for parallel is Q1 plus Q2 plus, this is Q1, this is Q2, this is Q3, and also HL1, they have the HL2 and HL3. Okay, so the HL is equal to HL1 is equal to HL2 and HL3. So this is the basic assumption in pipe parallel. Okay, so now because this is an operation and A and B are common to all pipes. Okay, so now we look at an example here. So they have the parallel pipe, two pipe. Okay, so pipe 2 has a length 4 times longer than pipe 1. Okay, so pipe 1 here and the pipe 2 here. Okay, both pipe has a same diameter. Okay, so which is 305 mm diameter for both pipe. So if discharge in pipe 2 is 1 meter cubic per second, find discharge for pipe 1. Okay, so calculate flow rate of system if F equal to 0.01 and a neglect minor losses. So neglect minor losses, no HM. So just only have HF. So now the solution here. Okay, so you first find the velocity. Okay, velocity here, they give you the velocity pipe 2. Okay, so velocity 2 they give you is the Q discharge. Okay, the discharge for in pipe 2 is 1 meter cubic per second. Okay, so you must find here. Okay, so that's why you must find the velocity because the Q for in pipe 2 is given as 1 here. Okay, and diameter for both pipe is 305 mm. So you just find the velocity 2. Okay, so you get this solution. Okay, so in parallel pipe, so we know that the HL1 is equal to HL2 and HF1 is equal to HF2. So that we know that the value here. Okay, okay, because neglect the HM, neglect the minor losses, so they have no HM. So they just only have the HF1. Okay, so the F1 is HF2 is equal. Okay, so you just put the value here. Okay, and HF2 here. Okay, using this continuity. So actually this is a continuity equation. Okay, F1 L1 V1 squared over 2G D1 is equal to F2 L2 V2 squared over 2G D2. Okay, so you get this formula. Okay, so we know that the give you here, the pipe 2 has a 4 times longer than pipe 1. Okay, so L2 over L1 is 4. Okay, for 2 is length 4 times longer than pipe 1. Okay, so the L2 over L1 is, so actually L2 is equal to 4 L1. Okay, so we get the L2 over L1 is equal to 4. Okay, that's why you get this formula. Okay, you get this value. Okay, and then you find the V2 squared over, okay, V1 squared. Okay, to get the V1 squared here, so you use the here. Okay, so Q1 is equal to A1 V1. Okay, so you get the the here, so V1 squared, so V1 squared. Okay, so you get 1 times by 4 times by 1 times by here, so you get the value here. Okay, 2GD here until you get this one. Okay, from actually this is from the V1 squared here based on this. Okay, based on this is the Q1 V1 is to get from this one. Okay, the V1 squared over here is based on from this formula. Okay, so you just put the F1 L1 V1 squared. So okay, 2G D1 is equal to F2 L2 V2 squared over 2GD. You just put here, and the L2 L1 here put to this formula. So then you just get the V1. Okay, based from this one, so you get this V1. Okay, after you solve this formula, okay, continuity equation, so you solve based on L2 L1 here for you get here. Okay, so F1 L1, okay, L2 and so on, so you get the value here. Okay, so that's why you get the V1 squared over 2G. 2G is you can, okay, and F1 and F2 is equal to the same formula, so you just only have L2 KV2 squared and D2 here, so you get the V1 is value here. Okay, so after you get the V1, so just put again in Q1 is equal to A1 V1. So you get the Q1 is 1.99 meter cubic per second. Okay, so that's you total up that for parallel. So total Q system is Q1 plus Q2. So you just plus that Q1 and the Q2. Okay, Q1 is 1 and Q2 you get the 1. So actually this is Q2. Okay, Q2, KA2 and the V2. Okay, so a Q1 and Q2. So Q2, so this is Q1 is 1. Okay, sorry, the Q2 is 1 meter. So the Q2 is the 1 meter. So this is Q1. Okay, so the Q1 is, you get the Q1 A1 V1. So you get the value of 1.99 meter cubic per second, and then you get the total Q is 2.99 meter cubic per second. So you get the value of this. Okay, so actually for this chapter 5 is to find the Q, discharge. Okay, to find the discharge based on the pipe. Okay, pipe system. Okay, based on the pipe system. Okay, so now we look at an example here. Okay, so this example based on using the US unit. Okay, 3 pipes A, B, and C. 3 pipes A, B, and C. Okay, so they have combined. Okay, combined 3 pipes A and B. A, B, and C are interconnected as in figure below. The pipe characteristics are as follow. Okay, so find the rate at which water will flow in each pipe. So find also the pressure at point P. All pipe lengths are much greater than 1000 diameters, so neglect minor losses. So no minor losses. Okay, so the AB is the parallel pipe. Okay, and C is from AB and then just series. Okay, so based on the ABC here. Okay, so this is in SI unit, sorry, US unit. So I will give you as assignment, okay, using the SI unit. Okay, after finish this chapter. Okay, so I will give you as an assignment. So now this is just look at the example here. Okay, actually this is based on the SI unit, the US unit. So this is the same concept. You must find from first. Okay, find first. Okay, the between the equation. Okay, energy equation between 1 to 2 here, because this is open to the atmosphere. So you must using the energy equation between 1 to 2 here. So we can know that the P1, okay, is 0. Okay, and P2 at the P2 is also 0. Okay, and the V1 is also 0. Okay, and the VC is this is at the VC. Okay, so they have no 0 here. Okay, because they have the velocity at this pipe here. So VC. Okay, so they have Z1. So Z1 to Z2. Okay, so 200. Okay, based on Z2. Okay, so Z1 is 200 here. Okay, and HFA is actually for the friction loss. Okay, in pipe A and also in pipe C here. Okay, based on the pipe C here. Actually, this is based on the series first. So we using the series. Okay, so HFA and the HFC here. So we put to the left side here. That's why we get the negative HFA and HFC here. So you get the value here and the value here. Okay, and put the Z2 and the VC2 squared over 2G. Okay. From continuity equation, so we know that the Q, because AB is the parallel, so the QA plus QB and the QC is series. So this part is the same, but QA plus QB is QC. So this is the from continuity equation. Okay, using the parallel and series. Okay, so VA plus AB VB is equal to AC VC. Okay, so you get this concept here. So you just get until you get this formula, okay, and put all the value here. So until you get the VA is 1.346 VC in terms of VC. So you get the velocity A in terms of velocity C, okay. For pipes in parallel, so pipe in parallel A, B here, okay. So we know that HFA is equal to HFB, okay. So we know that in parallel, okay, FA and AVA squared 2GDA is equal to FBLBVB squared over 2GDB here. Okay, so you just put the value of F, LA, FB, and LB. So until you get the value of VB. Okay, so VB in terms of VA. So you get the value of VB in terms of VA. Okay, so after you get this formula, so now we look at the VA here. VA is 1.346 VC. Okay, so use the energy equation between 1 and 2. Okay, so using the okay, after you just get the value here based on this here 200, okay, minus by this one. Okay, you just continue to the next slide. So we get the 150, okay, minus FA and AVA squared over 2GDA and F and VC here. So you get this formula and just put the value that you find from the VC in terms of VA and VA in terms of, okay, the value here, VB in terms of VA and the VA in terms of VB. So you get the VA here. Okay, just put here and then until you get the VC is 5.772 feet per second. Then you get the VA in terms of VC. So you get the value here. And you get the VB in terms of VA for this value. So then you get the QC here, okay, based on the AC, okay. And then you get the QA and you get the QB. So now the total for the Q here is QA plus QB is equal to QC. You just check that until you get the value of 2.015 here and is equal to QC. So you get this value, okay. So same as this value, okay. So just to check, so this is the concept, okay. So I will give you these questions based on SI unit, okay. So maybe I will change the feet to meter, okay. So you can do as assignment. So I will give you that as assignment too, okay. Now to get the pressure at point B, okay. So after you get settle using the energy equation, so use this, okay, formula that you find to get the P1, okay, pressure at point 1, okay. Pressure at point 1, sorry, pressure at point P is at the interconnection here, okay. So using the equation between 1 to P, okay. So to get the pressure at point P, so you must using the energy equation between 1 to P here. So you get the P here, okay. So you get the energy equation here. So you get this is also 0, okay. P1 is also 0, okay. PP, PP we have the PP here, and ZP is 120, and the VP is the VC here, okay. So you change here until you get this formula and then put all the value that you get and you get the value here, okay. So the P is this in feet here, okay. So you get the pressure at point P, okay. So you get this one, okay. Now we look at the pipe network, okay. The pipe network is distribution system, okay. Actually the pipe network we using the Hardy cross method, so that is your project, okay. So in municipal distribution system, pipes are frequently interconnected so that the flow to a given outlet may come by several different paths, okay. So as a result, we often cannot tell by inspection which way the flow travel, as in pipe BC. So the flow is based from the A, so this go to the D here and go also to B here and also go to the E here and F, C and G here. So this is called pipe network, okay, based on the distribution system, Okay, so there are simple methods to solve for pipe network in loops. Configurations are using the Hardy-Cross. Okay, so this is Hardy-Cross method. So using either Darcy-Weisbach or Hazen-Williams equation. Okay, linear theory and also Newton-Raphson. So in your project group, so you use the Hardy-Cross. Okay, so you use the Hardy-Cross. Okay, you use the Hardy-Cross method. Okay, you use this first method. Okay, so the most popular is the Hardy-Cross method, which involves a series of successive approximation and correction to flows in individual pipes. Okay, so now using the head losses equation, so the empirical equation which are Hazen-Williams, Manning and Darcy-Weisbach were rearranged into the form of head loss equation. So this Darcy-Weisbach, okay, using the HF is here, and the K here is 8FL pi, okay, 2G D5 here, N is equal to, okay, so we just put the HF, okay, HF is actually the KQN here, okay, the K, actually the KQN, so this is the value of K, and Hazen-Williams, so using this formula Hazen-Williams, and the K is here, so actually this is the K, and N is this one, okay, 1.85, and Manning here, okay. So for your project, so we use Darcy-Weisbach and also Hazen-Williams, so there's two types, okay. So Manning, so base and Mannings are using to get the N here, actually for get the N, okay. Now for using unit of measurement, so we just use the here, okay, so you just using the SI unit, okay. Okay, for Hazen-Williams, so we use the K as this here, okay. For Darcy-Weisbach, you just use the K is actually from this one, actually it's the same here, this FL here, okay, based on you just 8, okay, you just calculate 8, okay, divide by 3.1 for 2 squared, okay, and G, so you get the value here actually is the same here, okay, D5, okay, at the D5 here, okay, so you get this one, and then using the, so using the Hazen-Williams, so Hazen-Williams is also actually this 10.67, so just use the 10.7, so you just use the 10.70 L, okay, and C, you use the C as N here, okay, C as N, they have the N here, okay, so ada typo sikit sini, they have the typo error here, so they have the power of N here, okay, CHN, okay, so the N is 1.85, so you use the 1.85, and D is 4.87 here, okay, actually they have the N here, see, N is using the 1.85, so that's why you get this one, okay, so the same formula as this one, okay, the Darcy-Weisbach and the Hazen-Williams here, okay, so now using the pipe network, the flow in any network, however complicated, okay, must satisfy the basic relation of continuity and energy as flow follows. Okay, the flow into any junction must equal the flow out of it. Okay, so the flow into, okay, any junction must equal the flow out of it. Okay, so the flow in each pipe must satisfy the pipe friction loss for flow in a single pipe. Okay, the algebraic sum of the head losses around any closed loop must be 0. So the algebraic sum of the head loss around any closed loop must be 0. So this method called Hardy-Cross method. Okay, so procedure of Hardy-Cross method. First, you must divide the network into a number of closed loop. Okay, consumption are made for one loop at a time. Okay, compute K for each pipe. Okay, and trees assume a discharge QA and its direction in each pipe of the loop. Okay, and each join, the total flow in should equal to the flow out. Okay, so total flow in should equal. So the total flow in, okay, should equal to flow in should equal to the flow out. Okay, let's consider the clockwise. So the clockwise, this is clockwise is positive. Okay, and anti-clockwise is negative. Okay, so this is counter-clockwise or anti-clockwise flow to be negative, and clockwise flow to be positive. Okay, compute HF for each pipe and retain the sign of the flow direction. Okay, so you must know that retain the flow of direction. Compute HF divided by Q for each pipe without regard to the sign. Then determine the correction delta here. Okay, correction delta. Apply the correction algebraic, okay, to the discharge of each member of the loop. Okay, and for common members among two loops, both delta correction should be made. Okay, one for each loop. Okay, for the adjusted Q, repeat step. Okay, for adjusted Q, then you repeat again from step 4 to step 7. Okay, until delta become very small for all loops. Okay, so now we look at example here. Okay, so the example here, so if the flow into here and out of two loops, so this is, okay, this inlet, okay, this inlet, okay, and this is outlet. Okay, this is also outlet. Okay, so determine the flow in each pipe. Determine the flow in each pipe. Pipe here, okay, pipe here, pipe here, pipe here, okay, pipe here, here, pipe here, and here, and here, and also here. Okay, using only a basic scientific calculation. So the K values for each pipe were given, and N is 2. So K is given as here. Okay, K is here. Okay, K1 for pipe 1 here. K4 is for pipe here. K is equal to 4 for pipe here. And K for 3 is pipe here. And K is equal to 5 is pipe here. And K is equal to 2 is in pipe here. Okay, now you look at this solution first. Okay, as the first step, okay, assume, okay, you must assume the flow in pipe such that continuity hold at all junction. Okay, so take clockwise flows as positive. You just take that clockwise. Okay, this is clockwise is positive. Okay, anti-clockwise is negative. Okay, so calculate delta Q for each loop. Okay, make correction to assume QS. Okay, so repeat several times until the delta Qs are quite small. Okay, so first from the figure here, so you know that the inlet is 100. Okay, 100 cf, okay, cf cubic feet per second. So this is using the US unit. Okay, actually the US unit, cubic feet per second. So this is 100. Okay, and outlet is 25, and 100 is 50, and 100 is also 25. Okay, so and the K here. So now for assume, so this is for assume. Okay, so you assume first. Okay, so you assume, okay, assume a flow in pipe such that continuity hold at all junctions. So you assume that flow is based from the inlet here. So there's outlet 60 here and also outlet 240. So if you just plus here 60 plus 40, so you get the same. So you must remember that flow inlet, okay, flow in is equal to flow out. Maksudnya this is more balanced. Okay, for balance, flow in must equal to flow out. So that's why the flow in is 100. So flow out is also 100. They divide to 60 to 40 here. Okay, for this pipe and for this pipe. So this is the same here. Okay, now look at this one. So this is the outlet here is 25. Okay, so at that pipe here, this is 50. Okay, and also this is 60. This is 50. So and this is 10. Okay, so from this inlet here, inlet pipe here, inlet flow here, so you must out to 50 and out to 10. So if you just plus 50 plus 10, so you get the same 60 here. Okay, and so you get the 50 and the 10 here. So now you look at here. So this is 50. So the out is 25, so this also out is 25. Okay, so you just assume the direction of the flow. Okay, you assume the direction based on in and out. Okay, so based on the positive and the negative. Okay, so you just, okay, and then you look at the, this is inlet here. Okay, 40, and this is also inlet 10. So 4 plus 10, so you get the 50. So 50, so this is outlet to 25, so this pump is outlet to 25, so the 50, okay, same as 25 and 25. Okay, so you get the value. So this is inlet to 25, and this is inlet to 25, so you get the 50 here. Okay, so this is the correct, the first assumption. Okay, assume, so you assume, so you must assume first, you assume first the direction of flow. Okay, the direction of flow, so that's why you assume as this one to this one. So the this inlet, outlet to 60 and outlet to the 40. Okay, and then you, this is from 60, you outlet to 50 and outlet to 10. Okay, and 50 is outlet to 25 and outlet to 25. Okay, so it is 10 and plus the 40, 40, 10 plus 40, so you just get the 50 and outlet to 25 and outlet to 25. So the 25 plus 25, so you get outlet to 50. So you just assume first. Okay, now after you assume first here, so this is that you assume based on first approximation. Okay, that you assume from the previous slide. Okay, so now you just calculate. Okay, based on the HL is equal to K Q N here. So actually the HL is based on the, sorry, the HL here. So the, sorry, the HL of this one. Okay, based on the formula of Darcy-Weisbach or Hansen-Williams. Okay, so you get the HL here based on K times by the Q here. Okay, so K is based on the, but this K is based on the K here given here. Okay, so this is left loop. Okay, left loop is this loop. Okay, this loop is left loop. Okay, and this loop, okay, the blue loop here is the right loop. Okay, so they have two loops, so they have two loops. Okay, one loop is the red loop here, we just put as the left loop, and the blue loop here is the second loop, we just put as the right loop here. Okay, so now you just, first you must look at the left loop first here. Okay, so you just take the K, so this is the K1. Okay, K1 is the at this pipe. Okay, K1 is at this pipe. Okay, K1 here. Okay, K1, okay, and the K3 here at this pipe. Okay, so that's, you get the K3 here. Okay, and the K4 here. Okay, and that this pipe. Okay, so this is based on, so based on the clockwise. Okay, you get the positive. Okay, so that's why the K1 here is positive here. Okay, so this is clockwise is positive. Okay, so you just K times by the flow here. So the K1 plus, sorry, 1 times by the 60. So you get the 60 squared here because the N is given as 2. Okay, so N is equal, sorry, N is equal to 2. Okay, N is equal to 2. Okay, so that's why the N is for the Q power of N. So that's why the Q6, okay, 60 power times, okay, 60 power of 2 here, and the 4 here, the K3 is 40. Okay, 40 is like the anti-clockwise, that's why this anti-clockwise. Okay, and the 10 here, in the 10 here at this, okay, this length here is 10 here, so that's why 10, so you get the positive here. Okay, Okay, you solve here, so you get the 3600, and this is you get the 400, and this you solve that you get the 4800. Okay, so just plus 2 here, so just 3600 plus 400. Okay, and then you minus based on 4800, so you get the value here is negative. Okay, based on the flow direction here. Okay, based on the positive plus positive here, you get 4000, then minus by 4800, so you get the 800, so the direction is negative here. So this is left loop. Okay, after you put use the here, so you just look back again at the right loop. Okay, at the same calculation, at the same, you must calculate in the same time. Okay, so you must calculate also the left loop and the loop here. Okay, and the right loop here first. Okay, so you get the right loop here. Okay, and for the K4 is this one. Okay, and the flow is 50, so the 50 here, so the direction of the flow is positive here. Okay, with the clockwise. Okay, and the K is 2 here, so using the K2 here and 25 squared, so this also positive. Okay, the clockwise. Okay, and the 10 here, so the 10 is the same. Okay, this is the same as the loop 1 and the loop 2, because this is share. Okay, this pipe here is share with loop 1 and the loop 2. This pipe, okay, is share with loop 1 and the loop 2 here. Okay, so that's why the K4 here, so the K4 here is 4 times by the 10Q. Okay, the 10Q here. But for the at the loops 2, the direction here is negative. Okay, because it's anti-clockwise. Okay, and the K5 here is K5, and the Q is 25 here, so this is anti-clockwise also. Okay, so you just calculate. So 10 plus here, then you just minus 4 and minus here, so you get the value here. Okay, the value is positive. Okay, for direction. So now you look at this formula here. Okay, n times by the k, q, n minus by 2. Okay, and 2 minus by 1, so the power is 1. Okay, so n, k, n, okay, sorry, for the k, okay, so k times by the n here 2, n is 2 here. Okay, so this is k, this is n, this is q. Okay, q2 minus by 1. Okay, so you get 1 here, so you get until you get 1 2 0. Okay, 4 times by 2 and times by the 10 here, 10 is the q, so you get this value, and k times by the n times by the q. Okay, so you get the value here, so just plus here, you get this value. Okay, now after you get this one, so you must use the delta q. Actually, this delta q1. Okay, for the assumption 1. Okay, so you get the, from this is negative here. Okay, must the negative. Okay, must is the negative, but this is also negative, so just divide by the value here. So you get the value of 2. Okay, 2 is positive, so the direction is positive. Okay, for the right loop, okay, you just also use the n, k, q, n1 here, so you get the value here and value here and here, so you just total up, so you get the value here. Okay, so actually n is the k, this is k, this is N, and this is Q. Qn minus by 1. Okay, so you get the value, and then you get this is delta Q1 at the first assumption for the right loop. So negative here, this is positive, okay, and you divide here, so you just get negative, okay, because this is negative here, so you get anti-clockwise, okay. After first assumption, so you must do this based on delta Q here, you use here to second assumption. After first correction, this is second assumption, okay. Second assumption, so you must using the delta Q that you find from the first assumption, okay. So use the from the you get the delta Q here too, okay. So after you get the delta Q, so the new flow is, okay, this based on the 60 here, you just plus the 2 here, so just plus the 2, so you get 62, okay. And the 40, okay, 40 here, you this is negative, so you plus 2, so you get you get the value of 38, okay. And also the 10 here, so the 10 here, actually the 10 here is share with the loop 1 and the loop 2. So the 10 here based on the delta is you get 2, okay. And delta at the right loop is 9, okay. So you must plus, okay, plus 9 and plus 2, okay. So that's why you get the value of 21, okay. You get the 21 here, okay, because based on the 10, okay, plus 9, okay. So 10 plus 9, you get the 19, and you plus 2, okay. So you get the 21, okay. So you get the 21. That's why you get the 21 here, because this is the pipe that share with the loops 1 and the loop 2. So that's why you get the 21 here, okay. And the 38. So now at the 4 here, okay, at the pipe here is 50, okay. You just plus the 9 here, so you get the 41, okay, because this is positive but this is negative, so the 50 minus by 9, so you get the 41 here, okay. So this pipe here is 25 is anti-clockwise, but this is also negative, so you get the 16 here, okay, based on the, okay, because you get this is 25 here is positive, okay, positive and minus 9, so 25 minus by 9, so you get 14, sorry, 16, so you get the 16, okay. For the 25 is a negative anti-clockwise, and the negative here, so you get 34 here, okay. So you get the new, so you get the new flow, okay, the new flow in this pipe, okay. So you get the new, so you just do again the calculation for second assumption in the left loop and the right loop. So you just put the k is the value of k here, okay, and the value of n, q, this is k, this is q, okay. Just calculate again, so you get the value of this is plus, okay, and this is also the plus here, okay, and this is negative, okay. So you get the direction of the plus here, okay. Based on the, this is k, this is n, this is q, 2 minus by 1, so you get the value here, okay. So the value here and total up this one, okay, and you get this one. So then you just do again the delta Q2, okay, in second assumption. That's why you get the Q2, okay. Q is in second assumption, so you get the new value of 2 here, okay. Delta Q is 2, okay. And right loop, you just also calculate again based on the new flow here, okay, based on the K here and also the Q. Okay, so you get the value here, just total up of here. Okay, and the value here just based on calculate again. So this is must calculate again for second time. Okay, for second assumption, so you get the value of 0. Okay, until you get that one of the loop is 0, you can stop. Okay, so this is the two loops on this. So in two loops, you maybe one of the loop you get this 0, so you can stop. Okay, after one of the loop you get the delta Q is 0, you can stop at second assumption only, because this just only have two loops only. So that's why one of the loop have have 0. Okay, 0 delta Q in 0, so you can stop. So now the new flow in that loops, the branching pipe here is here. Okay, so based on the new, you get, sorry, the new, this is 2, this is 0. Okay, so the at this left loop, so you just 62. Okay, minus by 2, so you get the 60. Okay, 38. Okay, negative, and also negative 2, so you get 40. So the 21 positive and minus by 2, so you get the new. So you get the new, so you get the new flow here. Okay, based on the last, you get here. Okay, based on this, the right loop is this the right, okay, the right flow. Okay, based on the left loop, based on the delta Q here, you just use here. So you until you get the real flow that you calculate. Okay, after second correction, so you get the new flow. Okay, so this is the step by step to calculate based on loop. Okay, loop 1 and loop 2. Okay, left loop and the right loop. Okay, so the example, last example here. Okay, for example 5.10 here, pipe A, B, and pipe C, A, C, and AB, they just only one loop. Okay, so they just only one loop here. Okay, so find discharge Q in every pipe for the water supply system by using Hardy-Cross method and using Darcy-Weisbach equation. So this is using Darcy-Weisbach equation. No minor losses in pipe. Okay, no minor losses. So this is the length, the diameter, and friction factor. Okay, so you just use the try one. Okay, so use the pipe AB, pipe AC, and CB. Okay, so pipe AB flow, pipe, this is inlet. Okay, this is outlet, and outlet here. Okay, so you just use the pipe A, B, A to C, okay, and CB. Okay, so that's why you get the AB, pipe AC, and pipe ACB. Okay, so the diameter, you just put the diameter here and the length here, and the F based on this characteristic. Okay, based on the characteristic that given here. Okay, you just put to this table. Okay, and then you use the using Darcy-Weisbach. So this means using the Darcy-Weisbach. Okay, so using the Darcy-Weisbach equation, so you must use the Darcy-Weisbach equation here. Okay, so Darcy-Weisbach equation, so you must use the K here, using KFL divided by 12.10 d power of 5. Okay, and using the HF is based on Darcy-Weisbach here, and the K is here. Okay, and N is 2. Okay, so you use the Darcy-Weisbach. Okay, so you just use here. Okay, 8FL, okay, over 9. Okay, 2GD. Okay, 2GD and d power of 5 here. Okay, actually is based on the value of here. okay, for based on the value of K here, okay, the F, okay, 8 FL pi squared G D5 here, okay, based on the Racine back. So you just calculate the value is all the here until you get this value, okay, and then this value you get, okay. And the Q1 here, okay, actually the Q1 is based on the, you assume that, okay, you assume that Q at the first assumption here, okay, this is inlet is 10, okay, so you just assume that at the AB is 5, okay, maybe outlet 5 and this is also 5, okay, and this also this 5, so the outlet is this 3, okay, so the 5 is 3, so this is minus 2, okay, so if 2, so 5, and also 2 here, so outlet is 7, so you can assume here, okay, so you assume that this is positive, anti-clockwise is negative, so this is positive, so this is positive, so this is positive based on the inlet here, okay, base inlet, so this is negative, so this is negative because you must start at the inlet, so the from the inlet, so the direction of this flow is here, this flow is based on here, so you get the positive here, the direction of flow is based on anti-clockwise, so this is negative, okay, and 2 is also anti-clockwise, so this is negative, okay, so this assumption, so you get assume here, so you assume Q1 here, okay, the direction assume, okay, you assume the direction of flow, assume direction of flow, okay, that's you will get the positive, okay, and the negative and negative here, okay, based on AB, AC, and CB. Okay, now using the FH, HF is KQ squared here, okay, HF, okay, KQ squared based on the N, okay, actually the HF is based on K, Q, N, okay, based on this equation, okay, actually based on the here, okay, based on the HF here, okay, so that's why you use the value here, okay, and this is based on N times by the K, Q, N minus 1, so you get the value here, okay, you just solve the calculation here until you get this value, this value, and this value, and this value, and also this value, this value, this value, and this value. So from this, to get the dq1 here, delta q1, okay, so you must hf, okay, this one divide by this one, okay, so you get the negative 21697.37343 divide by 9748.8128. Okay, actually the negative is the direction of flow, okay, so don't worry about this direction, so you get the delta q1 is this 2.2257, okay, so the negative is just for the direction, okay, the direction of the flow, okay, so after you get the dq1 here, so you use that dq1 to using the trial one, okay, so delta q, okay, from the you get the 2.2257, so this is positive, so positive minus by the direction is negative here, so you just 5 minus by 2, so you get the sorry, you get the 7 here, okay, so actually this is based on AB and AC here, so this is negative, okay, based on the 2 here, so you get the here, okay, actually based on the trial here, okay, see, actually this is base plus negative here, so no, so this is no, this is positive, Okay, so you get the value. Okay, so based on you get the 2.2257, so the 5 plus the 2.2257 here, so you get the value of 7.23 here. Okay, 7.23, you get just 23 here, and negative 5 plus 2.23 here, so you get the negative 2.77. Okay, and the 2 here, negative 2 plus 2.23, so you get the value of 0.23. Okay, so now you just solve again to get this value, and this value. Okay, actually the value is based on the flow direction. Okay, flow direction, so you get the value, this value and this value. So now to get the dq2, so you must this one divide by this one, so you get this value. Okay, so you get this value as 1.06787, so you get this one. Okay, and the trial 3, so you get the delta q3, so use the q2. Okay, based on the 7.23, so you plus 1.06, so you get this value. Okay, and this negative 2.77, you plus here, so you get this here, and this one is, you get this quotient. Okay, so actually the negative is for the direction of the flow. Okay, so don't worry about that one. Okay, so you just go to the trial 3. Okay, until you get the delta q is 0.1576. Okay, until you get that one. Okay, so and then you get this one, you just try again to trial 4. Okay, and then after you get the delta q is based on 0.000 something. Okay, if in your project, okay, I mentioned that for your project is you can stop when each one of the loop or two of the loop you have 0.000x something. So for this case, okay, after you get trial 4 and you get the final here, until you get the value of delta q is 0.0000. Okay, you can stop the calculation. So the final q is based on the here, because you get the delta q is here. Okay, so the final, so you get the value of q in each pipe is this one. Okay, so this one is based on your calculate. Okay, you calculate here until you get the delta q is 0.000 something. Okay, that's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh. Okay, if you want to more understand, you can ask in our tutorial class. That's all. Thank you.